Let's investigate the quantum Fourier transform. First, we need to introduce some useful notation. Consider the non-negative integer denoted by x. We can represent the value of x as a binary string. Let's denote that binary string as x1, x2, ... xn minus 1, and finally xn. This little n is the length of this binary string. All of the values, x1, x2, all the way through to xn, can take on values of 0 and 1. So we have a binary string that's used to represent the value of x. Let's write this out more explicitly. This is equivalent to x1 times 2 to the n minus 1 plus x2 times 2 to the n minus 2 plus ... These are all the intermediate values. And then we have the last two values. So that is xn minus 1 times 2 to the 1 plus xn times 2 to the 0. We can write this more condensedly using summation notation. This is the sum over the index k going from 1 up to n of x sub k times 2 to the n minus k. So this is the pattern that all of these terms obey. So if we look at this term, for example, we're dealing with n minus the quantity n minus 1. So the n's cancel and the sign of this minus 1 gets flipped. That's why we have a plus 1 over here. And for this term, we have n minus n, which gives 0. And you can think of this term as the ones digit. So this is the ones digit, and then we have the twos digit, then the fours digit, and we go all the way up to 2 to the power of n minus 1. This is the highest power of 2 present in this binary representation. So this is a binary string, and that is condensed notation for this over here. And we can also write it in summation notation. Now let's consider the quantity x times 2 to the power of minus j. So we're multiplying this quantity x by 2 to the minus j. That is equivalent to shifting this string. So let's see what that looks like. We're going to have x1 ... all the way up to the value xn minus j. And over here we can put a point. So this is just like a decimal point, but we're not dealing with a decimal number, we're dealing with a binary representation. So for this point over here, we have a whole number. And now we're dealing with fractions. So this is less than 1. And this is going to be xn minus j plus 1. And then we can go ... all the way up to the final term, which is xn. So let's write this out more explicitly. What is this going to look like? This first term is going to be x1 times 2 to the n minus 1 minus j. So we're just subtracting j from this exponent. That is just an exponential law. Now we have to add all of those intermediate terms. So we can go ... and then we get to the term xn minus j. And this multiplies 2 to the power of 0. In this representation over here, if we had n minus j, we would have the exponent of j up here. But we're subtracting j. So we have j minus j, which gives 0. So that's the explanation for this term. So we have turned this term into the ones digit. 2 to the 0 is 1, so now this is playing the role of the ones digit. Then the next term is x n minus j plus 1, and that multiplies 2 to the minus 1. So now we're dealing with fractions. So we've gone from whole numbers to fractions. This is 1/2. And then the next term is going to be a quarter, and then an eighth. And then we're going to keep going on and on and on until we reach the final value, which is xn, and that multiplies 2 to the minus j. So up here, this used to have an exponent of 0, but now the exponent is minus j. So what is the pattern? We can see it if we write this in summation notation. We have the sum from k equals 1 to n of xk times 2 to the n minus k minus j. So all we're doing is subtracting j from the exponents for all of these terms. And that is equivalent to shifting this binary string. And let's consider a special case, that is x times 2 to the minus n. So we're setting j equal to n. That is the length of this binary string. What is that going to be? Well, that's the same as the sum over k from 1 up to n of this quantity. So we have xk 2 to the minus k. Why is it minus k? Well, when we set j equal to n cancels with this quantity over here. So we have n minus n, and we're just left with minus k. And we can write that in this format. We're going to have 0.x1 ... all the way up to xn. So we have shifted the entire string beyond this point. So this is just like the decimal point. We've turned an integer, which is a whole number, into a fraction. So it's less than 1. So this would be the ones place over here. And now we're dealing with 1/2, then a quarter, and then smaller and smaller factors, which are given by this exponent over here. So now that we have this notation for these binary strings understood, we can also write down a very useful property. If we take the complex exponential e to the 2 pi I, and inside this complex exponential, if we insert this value, we're going to have an interesting relationship. So let's have a look at x1 ... xn minus j, and then we put this point over here. So this is a whole number, and then we have the fraction portion. So this is less than 1, and we're going to have xn minus j plus 1 ... all the way up to xn. That's the final digit over here, the final bit in this string. And this over here, this is the important point. Beyond this point, we're dealing with a fraction. And this is equivalent to e to the 2 pi I times 0.xn minus j plus 1 ... all the way up to xn. And you can see if you have a special case where j is equal to n, you have n minus n over here. Those guys cancel, and then we just have x1 all the way to xn. So that's equivalent to having this representation inside here. So why can we do this? Why can we ignore everything to the left of this point? So that's this point over here. Everything to the left can be ignored. Well, it's because these guys are whole numbers. This is an integer. And if you multiply the factor of 2 pi by an integer, that's equivalent to going a full revolution around the unit circle in the complex plane. So that's the same as multiplying by 1. So imagine the complex plane, you have the unit circle, and this complex exponential tells you how you rotate around that unit circle. And if you have 2 pi radians, that's 1 full revolution. Any integer multiple of 2 pi is going to get you right back to where you started. So it's equivalent to the multiplicative identity. E to the 2 pi I is equal to 1. And 1 is the multiplicative identity. That's why we're allowed to make this relationship work. So now that we have this, I also want to write down another important relationship, and then we can actually define the quantum Fourier transform. So consider e to the I omega 1 multiplying some quantum state labeled by k1, and then we want to take the tensor product with another state, e to the I omega 2, and then we're going to have k2 over here as the label for this quantum state. We can use the exponential laws to group this together, and we're going to get e to the I omega 1 plus omega 2. So we've turned the product of exponentials into the sum of these arguments in the exponential. And then when we have the tensor product of these states, we can write this as k1, k2. So this is condensed notation for the state k1 tensor product with the state k2. And this k1 and k2, we can use a similar reasoning to what we have up here for x. We can define the quantity k, and we can represent it as a binary string. So this is the same as k1 ... all the way up to kn. And another quantity that is very useful to define is capital N. This is the same as 2 to the power of little n. So little n is the number of bits in this string. Or when we're dealing with quantum mechanics, it's the number of qubits. And big N is the dimension of the Hilbert space. So the number of qubits can be used to determine the dimension of the Hilbert space. All we have to do is take 2 to the power of the number of qubits, and then we get the dimension of the Hilbert space. Now we have all of this notation defined over here, so we can define the quantum Fourier transform. I'm going to use the notation f sub big N. So this is the quantum Fourier transform for a big N dimensional Hilbert space. And let's consider what this does to a computational basis state labeled by x. So x can be expressed as this binary string over here. And we can also express this value in decimal. But it's very convenient to work with this binary string, because then we can interpret each of these values as the value that we need to initialize a register of qubits. So all of these guys are going to be 0 or 1, and we can use that as notation for our computational basis states. And this over here, this is a computational basis state for the entire little n qubit system. So let's see how the quantum Fourier transform acts on this. We can define this as 2 to the minus n over 2. This is a normalization coefficient. Then we're going to use this tensor product sign, and we're going to have an index. Let's call that index j. J is going to go from 1 up to little n. And we're going to take the tensor product repeatedly for this following quantity. We're going to have the state labeled by 0, and then we're going to have e to the 2 pi I times this x over here. So the x is showing up here. And then we're going to have 2 to the power of minus j. And this j is the index that goes from 1 to n. And this is the coefficient of the state labeled by 1. So we take this quantity over here, which is specified by j, and then we take the tensor product of n copies of that. So we have n copies, and j is going to determine how this phase factor changes in each of those copies. And we can also write all of this stuff in the brackets in a more condensed notation. We can write this using summation notation. So let's do that over here. We can write this as 2 to the minus little n on 2, and we have the tensor product sign. The index j goes from 1 to n, and then inside the brackets, we can write the sum over an index k sub j. K sub j is going to go from 0 to 1. So here we have an index indexing another index. So we have k sub j. The value of j determines which of these k sub j's we're dealing with. And the next thing that we're going to write is e to the 2 pi I, and then we're going to have x, and then we need k sub j, that's this index, and then we're going to multiply this by 2 to the minus j. And this is the coefficient that multiplies the state, and the state is labeled by k sub j. So there's two options. We have 0 and 1. When k sub j is equal to 0, this exponential just turns to 1. So all of this 0 over here makes this equal to 1. And the label for the state is 0. So that explains this term. When k sub j is equal to 1, then we have a 1 up here. So that gives us this coefficient, and the label for the state is 1. So this is a summation notation format for this exact expression over here. These are equivalent. And the reason I've written it in this form is because now we can expand this out and we can pull out a bunch of summation signs. So I'm going to do that underneath. We're going to have this normalization coefficient is still going to remain there. We're going to have 2 to the minus little n on 2. And now we're going to actually apply this tensor product. We're going to take all of these n terms and we're going to apply the tensor product. So what is that going to do? We're going to set j equals to 1, then j equals to 2, and all the way up to n. So let's consider what's happening to these summation signs. We need to pull these summation signs out to the left. First, we have k1 going from 0 to 1, and then we can go dot, dot, dot. We have all the other summation signs up to kn, which goes from 0 to 1. So that's all of those summation signs that appear in all of those tensor product terms. Then let's consider this exponential factor. We're going to be multiplying n of these exponential factors. And now we can use this property over here to combine them together. So we can take the multiplication of complex exponentials and we can turn that into the sum of arguments. So we're going to have e to the 2 pi I x, that is common with all of these terms. And then the thing that is different is this part over here. So we're going to need the sum from j equals 1 up to little n of k sub j, and then we have 2 to the minus j. So this big sum over here is a result of multiplying n copies of this for all the values of j going from 1 to n. And what's happening to the state? Well, the state is going to be the tensor product of k1, k2, all the way up to kn. So we can write this as k1 dot 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 all the way up to kn. That's just a tensor product. So this is what happens when we apply the tensor product. We combine these exponential functions, and then we pull out all of the summation signs to the left. And now, instead of dealing with n of these little indices, which go from 0 to 1, let's just deal with one index k. Let's deal with this k over here. So we can relabel this as 2 to the minus n on 2, and then we can turn this into one summation sign. So we're going to have the sum from k equals 0 up to 2 to the n minus 1. So what does this k equals 0 correspond to? It corresponds to all of these bits being equal to 0. So we just have a string of all zeros, and that is what we're calling k equals 0. But we actually have 2 to the n terms, right? That's the same as capital N. We have 2 to the n terms, so we need to subtract 1 because we're including this 0. That's why we have a minus 1 up here in the top. So that explains the summation sign. Now let's collapse this exponential. So we're going to have e to the 2 pi I x, and this over here is the same format that we saw when we were defining this notation. So if you relabel this index j to k, and you relabel the variable k to x, you're going to see that it's exactly the same format. So we can rewrite this as k times 2 to the minus n. So we have k times 2 to the minus n. That's all up here in the argument of this exponential. So this 2 pi ix has remained unchanged, but this summation has turned into this. And then as the label for our state, we're just going to use k. So k is the label for the state, and it's also the index over here. So this is just another way of representing the value of k. K can be represented in decimal or in binary. Over here, we're representing it in binary, and all of those bits in this string are going from 0 to 1. So there's two values that they can have. Okay, now that we have this form, let's substitute big N. So let's write this in terms of big N. We can write this as big N to the power of minus 1/2. So you can see 2 to the power of n over here, and we're just relabeling it as big N. Then we can write this as the sum from k equals 0 up to big N minus 1. So this is big N up here. We have 2 to the n. And then we have e to the 2 pi I x, and we have k over here, but then we also have to divide by n. Or we could say we multiply by n to the power of minus 1. So n to the power of minus 1, that is present over here. This is the same as dividing this quantity by big N. And then we just have k over here. But we can also write this in another form. We can write this as 1 over the square root of big N times the sum of k going from 0 up to big N minus 1. So that's the same so far. But this exponential over here, we can relabel that as omega sub n. And then we raise this to the power of xk, product of xk. So what is this omega sub n? Well, omega sub n can be defined as e to the 2 pi I times n to the minus 1, or we are dividing by this big N. We can also write this as e to the 2 pi I times 2 to the minus little n. So this is equivalent over here. We're either expressing it in terms of big N or in terms of little n. So that is what this omega n is. And this format looks a lot like the discrete Fourier transform. And what we're doing is we're creating a quantum analog to the discrete Fourier transform. So this format looks very similar to what you would encounter in signal processing or in electrical engineering. The only difference is we're dealing with a quantum state over here. This is Dirac notation. We have a ket, and k is the label for this ket. But this format up here, the tensor product representation, is more convenient when we construct the quantum circuit diagram. So I'm going to write this out in full. So what is this actually equivalent to? Well, another way we can think of this is imagine that we start off with the state x. So this state x is equivalent to x1 dot 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 all the way up to xn. And we can also write this as x1 tensor product x2 tensor product dot 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 tensor product all the way up to xn. And the quantum Fourier transform, it turns this state into 2 to the minus n on 2. And then we have the first value, which is 0 plus e to the 2 pi I. And the first value we actually get is 0.x sub n. That's the first phase coefficient over here. So I'm just unpacking this definition. So this corresponds to j equals 1. And I'm writing this multiplication over here in this format over here. So that's exactly that we have this decimal format, and I'm using this property to get rid of all of the whole numbers. So when we first set j equal to 1, we're just doing one shift, and we only get this xn term. The next term, this is the same as j equals 2. We're going to get 0 plus e to the 2 pi I, and then we're going to have 0.xn minus 1, and then xn. So that's the next term in this sequence. And this is the coefficient of 1. And we can keep on going. So this would be the first one, the second one, and then finally, I'll write the final term in this sequence. So we have all of these tensor products, dot, dot, dot. The final term in this sequence is 0 plus e to the 2 pi I, and then we have 0.x1 dot, 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 all the way up to xn. And that is the final term over here. So this is this written out in full. So that's what this condensed notation for the tensor product representation is actually telling us. We have these decimals, and we're ignoring the integer part. We're only focusing on this fraction part. So over here, we're shifting by 1, then we're shifting by 2, and then we're shifting by n. So when we have the entire binary representation of the value of x. So that's exactly what we had up here. That's this quantity, and that's occurring in the final term. And we just have this normalization coefficient. So this is what the quantum Fourier transform does. It takes this computational basis state, all right, QFT. The quantum Fourier transform takes this computational basis state and it turns it into this, which we can also represent in this format, which is analogous to the discrete Fourier transform.